Section 6.6 is improper integrals. These are integrals that involve infinity in one way or another. So either infinity is in the limits of integration, or there's an infinite discontinuity along the interval that we're evaluating our definite integral. So type 1 is the first one. The interval is infinitely long. So our type 1 integral has an infinitely long interval of integration. And we see that as an example right here. We're trying to integrate the function sine of x dx from 0 to infinity, and that's an infinitely long interval, or negative infinity to infinity, or negative infinity to 0. Type 2, this is where an infinite discontinuity is within the interval of integration. These are a little bit sneakier. We have to keep an eye out to make sure that we don't overlook an infinite type 2 integral with an infinite discontinuity. We're integrating from 0 to 2 for this function, which seems harmless enough, but we have to remember that 1 minus x is in the denominator, so the value of 1 on that interval from 0 to 2 is actually a value of infinite discontinuity for our integrand, our function in the integral. And that could be, that could cause the integral to not converge. We'll see the definitions of those things in just a moment. So for the type 1 infinite integral, improper integral, if the integral from a to t of f of x dx exists for every number t that's greater than a, for every one of our possible values above a, then we can rewrite our infinite or type 1 integral from a to infinity of f of x dx as the limit as t goes to infinity of the integral of a to t of f of x dx. So remember, we can't handle infinity in any sort of algebraic way. Calculus has to do that for us. And we can't handle infinity within our function. Leaving it here is really symbolic of this process. It doesn't mean we're actually doing calculus with infinity here. We are doing calculus. We're not doing algebra with infinity. We're not going to find the antiderivative of this function and then plug in infinity to it. That's not possible. Okay, the way we go about doing that is evaluating the limit as t goes to infinity of this function's antiderivative. So it's very similar for negative infinity to b. We swap out the infinite portion of it as follows, and we arrive at this integral and limit situation. And at the very bottom, we've got the integral from negative infinity to infinity of f of x dx. And so the way we would split this is choose some value, and doesn't have to be in the middle, but somewhere in between positive infinity and negative infinity. You can pick any real number if that's the case then. And you can split the integral. Remember, we've always been able to split integrals. And you can evaluate from a to infinity, and then you can add the integral from negative infinity to a. Now remember, each one of these integrals needs to be interpreted in terms of these techniques above. So you have two different limits of an integral to take care of. So you have a limit of this one plus a limit of this one for the respective variables going to the respective infinities. So if the limit exists for such an integral such as this one, then we say that that integral converges. Same for this. If the limit does not exist for either of these, then we say that it diverges. Now for this to be true, we can only split up this sum if this integral and this integral converge. So in other words, these, when we split them into these parts, those two integrals in the sum converge. Once we know that these two integrals converge, then we know that we can split up this as these two sums. Typically in our operations, what we'll do is split this right away into these two type 1 integrals, and then we'll manage them with limits, and then we'll take those limits. If both limits exist, then both of these integrals converge, and then overall this integral will converge. If one of those has a limit that does not exist, then this limit does not converge. We just call it divergent. We should see some situations like this in the examples. So for an example of, see an explicit function here, from the previous page, our example was from 0 to infinity of sine of x dx. We immediately replace the infinite component here with an r we take the limit as r goes to infinity. So that's our typical workflow for these. From here, you'll notice that you can actually evaluate this integral in terms of limits of integration 0 to r, find the antiderivative of sine, apply those limits of integration, and then evaluate the limit from there. So if that limit exists, then that integral converges. Okay, so let's have a look at some examples to work. We're asked to determine whether or not each of the given integrals is convergent or divergent. So we've got the integral of 1 over x squared dx, and the limits of integration are from negative infinity to negative 1. So I'll rewrite 1 over x squared as x to the negative 2 when I rewrite my integrand, but I'll also write the integral swapping out this negative infinity component for an L and taking the limit as L goes to a negative infinity. So that's literally the definition of this integral, is to write it in this form. Without that, this integral, the circled integral, makes no sense. So we need to define it in these terms. Okay, working from here, we have a pretty standard antiderivative. The antiderivative of x to the negative 2, we add a power to negative 2, and we get negative 1 in that exponent. We divide by the new exponent, which is the same as multiplying by negative 1. And we evaluate from L to negative 1 our limits of integration. That being the case, we've got negative, this is the minus sign here, and then plugging in negative 1 for our upper limit of integration to the negative 1 power, and then minus negative L, our lower limit of integration, to the negative 1. And when we look at this, we realize that this is 1 over L, and it's plus 1 over L. And also, this is negative 1 to the negative 1 power. Well, to the negative 1 power just makes it 1 over negative 1, and the double negatives here make it positive, so it's just positive 1 plus 1 over L. And now we take the limit as L goes to negative infinity. And what that's going to do is it's going to drive this expression, well, L is going to go to negative infinity, so the denominator is going to grow larger and larger. So this expression, the limit as L goes to negative infinity, 1 over L is going to approach 0 from the left, or we just say that it's equal to 0. And using a limit law sort of implicitly here, we know that the limit of 1 as L goes to negative infinity is 1. Just kind of rehashing those old limit laws. So 1 plus 0 is equal to 1, and this integral converges. Not only do we know that it converges, but we know that it's equal to 1. So we're able to make this connection all the way through. And that'll typically be the case with these. If it converges and when we go directly to this method, we're going to find what it converges to. We will have one method, a convergence test, to prove whether or not an integral converges or not. Okay, so another one, same limits of integration, negative infinity to negative 1. We have 1 over x dx. And this is, again, immediately we pull that negative infinity out, swap it for an L, take the limit as L goes to negative infinity. So now we proceed as we normally would. The antiderivative of x to the negative 1 is natural log of x, and evaluate along our limits of integration from L to negative 1. Doing so, we've got natural log of negative 1, the upper limit of integration. Notice that 1 over x always integrates to the natural log of the absolute value of x. So we're prudent to write that there, and we've got it in our subsequent step here. And then minus natural log of the absolute value of L here. And in both cases, L is going to negative infinity. Again, this is a constant. Absolute value of negative 1 is 1. The natural log of 1 is 0. E to the 0 equals 1, so the natural log of 1 equals 0. Remember those as inverse functions. Now, minus natural log of L is still left in our expression. And what we see at this point is we have 0 minus natural log of L. L is going to negative infinity. And really, this is the absolute value of L. So what's happening is we plug in larger and larger values, larger and larger negative values of L, in other words, letting L go to negative infinity, is we're actually plugging larger and larger values going to positive infinity into the natural log. And the natural log has this shape, right? It doesn't increase very swiftly, but it certainly goes to infinity as x goes to infinity. And that's how we're able to establish that the result of this is 0 minus infinity. So this is actually equal to negative infinity, or better to say, this integral diverges. The limit, this one does not exist. So it diverges. Okay, so next step, or next problem to see, we have powers of p. So this really begs the question, or this sort of answers a question that the first two problems might have begged. 1 over x squared from negative infinity to negative 1 converged, but negative infinity negative 1 of 1 over x, this integral diverged. So there must be some sort of cutoff somewhere. So let's have a look at that. And this asks us here to determine which values of p this improper integral converges for or diverges. So if we let I be our integral, we swap out positive infinity for r, take the limit as r goes to infinity. Notice we're doing the positive version now. Essentially the same thing is true for the positive as is for the negative. We're just seeing it here from positive half now. And we've got x to the negative p dx for p not being equal to 1. That's the only special case, right? Because if p is equal to 1, we've got 1 over x. We know that that evaluates to the natural log. That will be the case that diverges, right? We've seen that on the previous page. I'll let the reader establish that for p being equal to 1 or even less than that too. We just we'll discuss that in a moment. Now, let's proceed with the special case that we're not worried about. If p is not 1, okay, then it's x to the 1 minus p. We add 1 to the power of x to get the antiderivative, and then we divide by that new power for our coefficient. So that's the factor of 1 over 1 minus. So to recap, we've got the limit as r goes to positive infinity. X to the 1 minus p. Our antiderivative has allowed us to add 1 to this exponent, and we divide by this new power, and that's our factor of 1 over 1 minus p, and our limits of integration are from 1 to r. Note that we've excluded p equals 1. It's the only case that we can't handle through this version. We know, or we've seen, that a natural log will show up, as in the previous example, and I'll let the reader confirm that in that case, this integral diverges when p is 1. It's very similar to what we did in the previous example. Now, factor out this constant multiple of 1 over 1 minus p. It's constant with respect to r, so it can factor to the front of the limit. And we evaluate our function x to the 1 minus p at r, it's here, and minus our evaluation at 1. So r to the 1 minus p minus 1 to the 1 minus p. Well, 1 to the 1 minus p is just 1. And r to the 1 minus p as r goes to infinity. Well, if p is greater, if 1 minus p is less than 0, so in other words, if p is greater than 0, then this number is negative, right? If p is greater than 0, then 1 minus p is less than 0. Sorry, if p is greater than 1, then 1 minus p is less than 0. Okay, and if 1 minus p is less than 0, then as r goes to infinity, this is 1 over r to the p power, or to the 1 minus p power. It's a negative power, so it drives this thing to 0. This one just remains negative 1, and we end up with 0 minus 1 times 1 over p. On the other hand, if 1 minus p is greater than or equal to 1, we've already know that, or the reader can show that when p equals 1, the natural log limit is going to diverge. If 1 minus p is strictly greater than 0, In other words, 1 minus p is positive. If 1 minus p is positive, this is r going to infinity with a positive power. That's going to drive this term overall to infinity, and our integral is going to diverge. So to recap all of this integral is equal to 1 over 1 minus p whenever p is greater than 1, and it diverges for any other value of p. So this is nice to refer to. We can use this for our comparison test for improper integrals that we'll see later in this section. Okay, discontinuous integrands. So this is the sneakier case. This is where we look at the interval from a to b, and we're integrating f of x with respect to x. And we find that there is some discontinuity. Well, in this case, we see that it's at b. We've put it at that right endpoint just to start. Well, we can split this up and get rid of b, the troublesome point, and write it as t approaches b from the left. Of course, we go from a to b. We're approaching b from the left in this limit of integration. So when we swap out b for t, we approach b from the left. Okay, and that helps us define this integral, even though an infinite discontinuity is involved. Okay, some of these will converge, some of these might not converge, just like the type 1. Similarly, for a being the point of discontinuity, then we do the limit as we approach a from the right. B is to the right of a, so we approach down to a. So t approaches a from the right side, goes downward towards a. If either of these limits exist for whichever function we might be dealing with, or whichever situation we might be dealing with, then we say that the integrals are convergent, or the integral is convergent. If the limit doesn't exist, then it's not divergent. Okay, if f has a discontinuity at c, and c is between a and b for some integral, then how we deal with this is we split it up. We go from a to c for this portion, and then we go from c to b for this portion. And from a to c we have an integral, and from c to b we have an integral. And together that makes up the overall integral from a to b. Now, of course, for each of these a to c and c to b integrals, this one's going to correspond to our first one, where the limit of discontinuity is on the right, and this one corresponds to our second one, where the limit of discontinuity is on the left, or the point of discontinuity is on the left. So that's how we handle that. We'll split the integral up over a point of discontinuity and work from there with our two single integrals. So let's have a look at one. Now we can see how sneaky this could be. It is possible that a reader who doesn't catch this could evaluate this to a number, and it in fact does. If we carry out this integration without being careful about the fact that x equals 6 is an infinite discontinuity for this integral, we would actually evaluate this and come out to a real number, and we'd be absolutely wrong. So let's keep that in mind. X equals 6 is not in the domain of this function, this rational function. So it's an infinite discontinuity, and some might remember that as a vertical asymptote. Okay, so what we do is we need to split our integral from 5 to 8 up as from 5 to 6, and then from 6 to 8 to complete our full interval of integration. Now we've got a point 6. So if we want to approach it from the left in this integral, we want to approach 6 from the right in this integral with some variables t and s is what we've used in this case. So now we've swapped out 6 here for t. We approach 6 from the left, from 5 up to 6. Similarly here, we swap out 6 for s, and we approach 6 from the right, from 8 down to s, or down to 6. Okay, now we just take our antiderivatives, or find our antiderivatives here. If needed, you might want to use a u substitution to handle the x minus 6, but since du is equal to dx, it's pretty straightforward. But a power rule increases -3 to -2 in both of these integrals, since it's the same antiderivative. And we divide by the new power, so it's 4 over this -2, and 4 over -2 is -2. Same thing happened here. 4 over this new power of -2 left us with that -2. And all that's left to do now is evaluate the integral for each of these, or sorry, the limit for each of these. And the limit as t goes to 6 from the left. from 5 to t. Well, let's evaluate first our limits of integration. Then we'll assess the limits. Getting ahead of myself. So -2 times the limit as t goes to 6 from the left is evaluation at t. We've used that negative exponent to just push this factor down to the denominator. And same thing here, 1 over 5 minus 6 squared in the denominator. And similarly over here, we have 1 over 8 minus 6 in that term in the denominator squared. And similarly, 1 over s minus 6 squared. Okay, so we're looking at 6 going to the t approaching 6 from the left. If this is the case, then t is getting closer and closer to 6. Remember, this is 6 from the left, not -6. So we're putting values of t that are closer and closer to 6 into this integral. And what we're getting out of that is it's getting closer and closer to 0 in the denominator. And that's pushing the whole thing, the whole fraction, to get closer and closer to infinity. So this one diverges. And really at this step, we're done because one of the two limits for these two integrals, has diverged already. There's no more work to do. But the reader can also confirm that this one diverges as well. Again, for the same reason. We're plugging in numbers closer and closer to 6. That denominator is getting closer and closer to 0, which drives the whole fraction closer and closer to infinity. So one last one to see in terms of splitting these integrals up and actually doing integration and finding the value if one exists is this, from pi over 2 to pi of cosecant x dx. Again, be very careful. You want to recognize where there might be a point of discontinuity or an infinite discontinuity for this function, and that's at pi. Remember that cosecant of x is 1 over sine x, which isn't all that bad until you realize that sine of pi is 0. So cosecant of pi is undefined. That's where it has a vertical asymptote. So that's the troublesome point. So we'll swap it out and we'll let t approach pi from the left, and it replaces pi in that limit of integration. And now we take the antiderivative of cosecant of x. If you recall from a few sections ago, the antiderivative of cosecant of x is natural log of cosecant x minus cotangent x. There's a trick to finding that. It is in the book, and you can just kind of keep track of it. If you know how to do it, that's great, but it's just like finding the antiderivative of secant of x. It's a very similar trick substitution or integration factor. Okay, so here's our antiderivative. Limit as t goes to pi from the left. We have pi over 2 to t, so let's apply our limits of integration. We have natural log cosecant t minus cotangent t minus natural log cosecant pi minus cotangent pi. Okay, all that looks good. At least this latter half that's highlighted now is easy to calculate. Cosecant of pi over 2 is 1 over sine of pi over 2. Sine of pi over 2 is 1, so that's 1 over 1. Leaves us with a 1. Cotangent of pi over 2 is cosine of pi over 2, which is 0, over sine of pi over 2, which is 1. So it's 0 over 1, and we get 0. Write all that out if you need to, but you should find that we get the same values I have down there. Now we've left this one fixed for now. And we see that 1 minus 0 is in the argument of natural log. So that's going to be the natural log of 1. And the natural log of 1 is 0. Remember, e to the 0 equals 1. So natural log of 1 equals 0. They're inverse functions of each other. So lastly, what we're left with is to consider the limit as t goes to pi from the left of natural log cosecant t minus cotangent t. So it would help to realize that this is 1 over sine of t, and this is cosine t over sine of t. So let's get a common denominator of sine of t. And we have 1 over sine of t, that's cosecant's portion, minus cosine of t over sine of t. So we have 1 minus cosine t over sine t overall. So as t goes to pi from the left, cosine of t is going to approach 0. Oh, sorry, -1. So this is 1 minus -1. So the top is approaching -2. Natural log of the absolute value of -2 over, well, the bottom, on the other hand, the denominator, as t goes to pi, sine is going to go to 0 as t goes to pi because sine of pi is 0. So we've got something approaching -2 in the numerator divided by something approaching 0 down here in the denominator. So that's -2 over 0, but we don't write that. We just call this approaching positive infinity because that -2 becomes positive with the absolute value bars. 2 over something going to 0 is approaching positive infinity, and the natural log of something that approaches positive infinity is positive infinity. Okay, our last topic for this section is the comparison theorem. And we suppose that we have two functions, f and g, which are continuous, and f of x is greater than or equal to g of x, and they're both positive for all x greater than some a being the lower limit of integration for a type 1 integral. Okay, a very similar theorem exists for type 2 integrals. It also exists for negative infinity to a. Okay, so that is an optional thing to use if needed in the future. With this theorem, we can't find what a convergent integral, improper integral might have as a value, but we can determine whether or not it converges or diverges possibly. So let's look at the situation. If this function from this integral from a to infinity of f of x dx is convergent, we know that f of x is greater than or equal to g of x. So without proving this theorem, we can kind of see that, of course, the area underneath this curve, if it's finite, that's what this convergence means, then the area underneath this integral must be finite as well, because g of x is less than or equal to f of x. So that's the gist of the proof of that theorem without actually getting into the proof. Now, on the other hand, if the smaller function, if g of x from a to infinity is divergent, then f of x from a to infinity, its integral is divergent as well, because f of x is a greater value than g of x, so it's going to be driven to infinity because this one underneath it is going there anyway, it has infinite area underneath it to begin with. Now, so let's use this comparison theorem. We have 0 to infinity, arctangent of x over 2 plus e to the x dx. So first things first, let's get rid of that positive infinity, swap it out for limit as r goes to infinity, put an r there for the upper limit of integration. Now, what we want to do is pick out something we can bound. And we know that arctangent of x is bounded by negative pi over 2 on the left for all x, and it's bounded by positive pi over 2 on the right for all x values. So have a look at a trig textbook, or go back to the Calc 1 section of our textbook and look at inverse trig functions. It should be a nice review of those. So since this is a bound on arctangent of x, what we want to do is try to reconstruct the integrand here within this set of inequalities. And to do so, in our case, looks like, well, one thing to note first is that if we're going from 0 to r, arctangent of x is greater than or equal to 0 for all x values that are greater than or equal to 0. So arctangent of 0 equals 0. And then if we put anything positive, it's always going to be positive. So we can immediately increase this bound on the left by a little bit because we're not going to plug in anything less than 0. So we've got 0 here on the left, and we divide both sides of this, or all sides really, of this series of inequalities by 2 plus e to the x. And the reason we do that is because we want to regain this denominator so that we can talk about bounding this entire term here. Okay, so doing so, we end up with 0 still here, and we've got pi over 2 over 2 plus e to the x. Okay, so what we're angling towards, it looks like, once I get to here, I start to think to myself, okay, well, I've bounded my function above by something. Below it turned out that I've got a fixed bound. So it doesn't seem like I can prove, at least with this inequality, that this function diverges, because I know that this doesn't diverge. The integral of 0 from 0 to infinity is 0. So I couldn't prove that this diverges with this inequality. I've used an appropriate bound. So if I can do anything with this, I can prove that this function, since it's less than this one, I might be able to prove that this one's integral is convergent. But first I need to know whether or not this is convergent. If the integral of this one is convergent, then I know through our comparison theorem that the integral of this one is convergent. Of course, that's on 0 to infinity for all those integrals mentioned there. Okay, so the next thing to do would be to realize that 2 plus e, so just simplifying our work a little bit further even, we know that 2 plus e to the x is greater than or equal to e to the x. I don't want to have to deal with the 2 in the denominator, so I'm tricking this up just a little bit further, even though it's not totally necessary. So this implies that if we flip both sides, we flip the inequality, and we have 1 over 2 plus e to the x is less than or equal to 1 over e to the x. Now, if that's the case, I know that this term is less than this term. So then pi over 2 plus e to the x is less than pi over 2 over 1 plus e to the x. Just multiplying by that factor of pi over 2. And well, 1 over e to the x is e to the negative x. So now I've got a nice clean bound that I can use or a nice clean function that I can check to see if its integral from 0 to infinity converges. Right? I have a good feeling about it because it's an exponential function and it's got a negative exponent. As we're going to positive infinity, this function is going to be driven to 0, and it's going to be driven to 0 rather quickly. So let's double check though. That's on the next page. So observe that we integrate this function from 0 to infinity. We swap out positive infinity for r, take the limit as r goes to infinity. Antiderivative of e to the negative x is negative e to the negative x. You might want to use a u substitution to be sure of that. Or you can double check that the derivative of this is positive e to the negative x. That's sufficient as well. From 0 to r, limit as r goes to infinity. So this is e to the negative r minus e to the 0. We've taken the minus sign and pushed it out here. Now the limit as r goes to positive infinity of e to the negative r, well, that's 1 over e to the r, and r is going to positive infinity, so this is being driven to 0. Now e to the 0 is 1, and the limit of 1 is just 1. So there's our minus sign in between. So negative pi over 2 times 0 minus 1 is the result of our limit, and that's just positive pi over 2, and we note that that's less than infinity. So this integral converges. And now we know from we can use the comparison theorem, knowing that this integral converges and it's a bound for this function. Well, the comparison theorem really tells us that this integral is less than or equal to this integral. And if this one converges on the right here, then the one on the left has to, because it's necessarily less than the other one. And so we conclude that this integral converges by the comparison test. So the comparison test is the trickiest thing perhaps that we've done so far. It takes the most in terms of thinking your way through it and planning ahead in a problem. But we were going to see more things like this in chapter 8 when we deal with sequences in series. So don't dismiss this now. I know it's only 1 or 2 questions on major assessments for this exam and for this block of material, but it's going to be very important later on. So definitely get a hold of this and learn how to do it.